Okay, welcome back everyone from the lunch break. So our next speaker is Chris Potts from Stanford. Now, unfortunately, due to travel, he doesn't have good internet connection, and so and also is some seems to be some chaos in his travel plans. So um, he provided us with a recording, so to be safe and turned out to be a great idea. So we're going to um, play his talk, but let me introduce him. So Chris is a professor of linguistics and computer science and chair of the Stanford Linguistics Department. Among other things, he has done highly influential work in natural language grounding, and semantic theory and compositionality in NLP, including a book, The Logic of Conventional Implicatures. Right, we'll now see his talk.
Hello, I'm Chris Potts. It's wonderful to be here with you all. My focus today will be on achieving faithful, human-interpretable model explanations using a family of techniques that we call causal abstraction. I'm here as a kind of representative of a much larger group of researchers at Stanford and elsewhere who are focused on these questions of model explanation. I'm going to do my level best to channel the collective wisdom of this very talented group of researchers. I want to say right at the start that I think model explanation is a crucial project for modern AI, and here's why. In this era of ever-expanding influence for our ideas, we as a field have quite rightly turned our attention to some really important high-level goals. For example, we would like to identify approved uses for our models and relatedly certify that a model will be safe and trustworthy for a particular deployment scenario. We also have more focused goals in mind, like identifying and possibly mitigating social biases that our models manifest, and maybe more generally, strategically editing models to correct mistakes that they're making and update them as information about the world changes. And I'm sure you can add other goals to this list. It seems to me that fundamentally this list is presupposing that we can offer analytic guarantees about how our models will behave. After all, it just seems foolhardy for me to certify that a model is safe and trustworthy for a particular use if I can't even tell you how it processes and stores information. And this is maybe even more dramatically true for use cases like mitigating social biases and editing models. Those are cases where I'm going to perform a surgery on an existing model. And if I can't even tell you where and how the relevant information is stored, it seems very likely that this surgery will simply kill the patient. Now, to date, by and large, the field has responded to these challenges in a familiar mode of continued behavioral testing. And what I mean by this is a kind of generalization of the train test methodology that we've seen for decades in the field, where now these test sets that people construct are meant to explore model properties, maybe test hypotheses about model behaviors, and often challenge models with adversarial cases that are meant to stress test the system and identify its shortcomings. This is a very powerful mode of inquiry, and everything I say today should be construed as complementary to these efforts in advanced behavioral testing. But I think you can hear in my description that there is an intrinsic weakness to behavioral testing. It is very good if I want to show you that a model has a social bias or show you that it is unsafe for a particular deployment scenario. But if I want to prove for you that a model is free of a social bias or safe for a particular scenario, behavioral testing is intrinsically limited. I think we're all aware of this at some level. It goes under the heading of the limits of scientific induction, but I would like you to feel it in your bones for the rest of this talk. And so let me linger over a simple example. On the slide here in this big black box, I have even odd model 1. This model is going to take in English strings referring to numbers and make a prediction about whether that number referred to is even or odd. So 4 comes in and even odd model 1 says even, 21 and it says odd, 32 and it says even, 36 and it says even, 63 and it says odd. At this point, the behavioral testing is going great and you might feel like you have a true model of even odd detection. But then I show you exactly how the model works. I illuminate the black box, and this gives you a flash of insight. You can see immediately that this is not a good model. It is a simple lookup table. We got lucky with our first 5 inputs, and you now know exactly how to foil this model. This else case gets triggered with odd, and so you input 22, and it makes a wrong prediction. The insight did not come from the behavioral testing, but rather from your opportunity to look at exactly how the model works. Let's move to model 2. Suppose it gets all these cases correct, gets 22 correct, 5 it says odd, 89 odd, 56 even. Is this a true model of even-odd detection? Our behavioral testing is going great, but then I show you how the model works. Again, a flash of insight. This is also not a good model. It's better than the first one. This one tokenizes its input and uses the final token as the basis for prediction, but it has this else clause here, and now you know exactly how to foil it. For example, 16 will do, it makes a wrong prediction there. Again, the behavioral testing is a kind of afterthought to the insight that you got from seeing exactly how the model works. Now we move to model 3 for even-odd detection. Is this a true model for our task? Well, we have an infinitude of possible inputs that we could consider, and in principle, we'll have to check all of them to get an absolute guarantee if we're going to just move in the behavioral mode. What we really need for a guarantee is to have the workings of this model illuminated. Now, here's the rub. As we all know, modern AI models are not like this transparent model that I've been showing you, which is nicely symbolic and easy to interpret. Rather, they're just messes of matrix multiplications at a vast scale, and it's very difficult analytically to understand how they store information. We might have a dream that we could crack them open and see transparently in the parameters a bunch of human interpretable concepts, but I think we know that this is not going to happen. When we crack them open, we see just an ocean of parameter values, and it's very difficult analytically to see how they're representing and storing information. But I'm optimistic. This is a thriving area of research, and I do think we will uncover some instruments that illuminate these black boxes for us and give us the kind of guarantees that we're seeking. I put these under the heading of structural evaluation modes. These complement the behavioral ones, and these methods include at least probing, feature attribution, and intervention-based methods. I would love to talk with you in detail about probing and feature attribution, but time is short, and so I'm going to focus in on these intervention-based methods. In this family of methods, we systematically alter the representations of our models to put those models in counterfactual states that help us identify the causal role of those explanations. And in this way, with a lot of interventions, we can piece together an understanding of the causal dynamics of even our most complicated models. So let's set ourselves some goals for this talk and maybe in general for the field. Goals for model explanation. The explanations we offer should be verifiably faithful, and both parts of that are important, faithful and verifiably so. These explanations should also be human interpretable. After all, I can give you a precise causal story about how these models work by simply walking you through all the matrix multiplications and other low-level operations that comprise these computations. But that's the wrong level to operate at if we want to address those really important goals that I stated at the start of the talk. We need human interpretable concepts, human interpretable explanations. And we need these explanations to be causal. We should move beyond mere correlational analysis to really illuminate the causal dynamics of these systems. I feel that model explanation methods should also offer a path to improving our models. Too often in this field, we observe that a model has some strengths and weaknesses, and then you say, well, how do I correct the weaknesses? I think the best of these methods will offer a smooth path from an insight about a weakness to addressing that weakness. We also need these methods to be scalable. We want to apply them to the most important models in the field right now, and those tend to be very large models indeed. And finally, these methods should make minimal assumptions about how information is encoded in these models. We just don't know a priori how they're going to store and represent human-level concepts if they do. We should make minimal presuppositions about how that would happen so that we can discover in a free-form way what these models have learned. All right, so let's move to talking about causal abstraction. This is the theoretical foundation for the talk today. And I begin with a sort of recipe for analysis in this mode. Step one for causal abstraction is to state a hypothesis about some aspect of your target model's causal structure. And you could express this hypothesis as a computer program or as a Bayes net, typically something structured like that. In step two, you search for an alignment between the causal model and your target model. And what this really comes down to is looking for alignments between variables in that causal model and sets of neurons in the target model. And to assess those alignments, you perform interchange interventions. That's really the fundamental operation of causal abstraction analysis. And let me unpack what interchange interventions are like by way of a simple example. So on the slide here, I have a very simple neural network. It takes in 3 numbers and it adds them together. And let's assume that this network performs its job perfectly. And our question is, how does it achieve this astounding level of success? So for causal abstraction, step one is to state a hypothesis about that neural model. And that's expressed as the causal model that I've given in green here. The essence of this is that the model adds together the first 2 inputs and stores that value in an intermediate variable S1. Then it copies over the 3rd input into an intermediate variable W, and then S1 and W are added together to form the output for the causal model. So it's a simple tree-structured model, and that's a hypothesis about how our neural network might be solving this task. Step one for interchange interventions is to think about an alignment. And in this case, we're going to align S1 in the causal model with L3 in the neural model. That represents a hypothesis about the causal role that L3 plays in our target model. The interchange intervention analysis begins by processing examples with the causal model. So we process 1, 3, 5, and we get the output 9. We use that same causal model to process the inputs 4, 5, 6, and we get 15. And then we target that S1 variable in the second example, and we take the value there and put it into the corresponding place in the first example. Having performed that intervention, we know exactly what the output of the causal model will be. It will change to 14, because all that matters in this case are the values of S1 and W. That's all as expected. We assume that we completely understand this causal model. Where things get interesting is when we turn to the neural model. We're going to perform a parallel intervention. So we process inputs 1, 3, 5 with the neural model. We use that same neural model to process the inputs 4, 5, 6. And then we target that L3 hidden state and literally take that value from the second example and put it into the corresponding place in the first network. And if, having performed that intervention, the network now outputs 14, then we have one piece of evidence that L3 and S1 are aligned in their causal roles. And if we repeat this intervention for every possible input to the network, and we always see this correspondence between the causal model and the neural model under the interventions, then we have proven that L3 and S1 play the same causal role. We could continue for other variables. For example, suppose we hypothesize that W in the causal model plays the role of L1 in the neural model. Again, that's a hypothesized alignment. We perform an intervention on the causal model, and we record the output value. That much is straightforward. Things get interesting again when we turn to the neural model. We target L1 in the second example and literally take that computed value and put it into the corresponding place in the first example. And as before, if that leads to the output 10, we have a single piece of evidence that W and L1 play the same causal role. And if every set of inputs to the network and the causal model leads to this aligned outcome, we have proven that W and L1 play the same causal role. And this extends to states that don't play a causal role. For example, suppose we perform lots of interventions across all possible inputs on the L2 state in the neural model and find that it never affects the input-output behavior of the model. That will amount to a proof that L2 plays no causal role in the network's behavior. And in this case, we can assume that the inputs are aligned across the causal and neural models and that the outputs are aligned. And so in essence, in piecing together all these interchange interventions, we have conducted a complete analysis showing in this case that the green model there is a good causal abstraction of the underlying neural model. So that is the essence of causal abstraction analysis using interchange interventions. And I do think that the interchange intervention is a particularly interesting data-driven intervention that we can perform in service of model explanation. but you've probably realized by now that it's by no means the only interesting intervention. For example, for years in the field, people have perturbed model representations as a kind of robustness check. That is a kind of intervention, and it even has a clear high-level causal model behind it. In this case, we're probably testing the hypothesized causal model of output invariance under those perturbations. And to the extent that the neural network realizes that causal model, it's robust to the perturbations that we're employing. Another common intervention is zeroing things out. In this case, the high-level causal model might be that we think information is stored at the point in the network that we're zeroing out, and therefore we expect that information to be in some sense neutralized. But another high-level causal model that might be guiding this is that we think that the information that we're zeroing out is irrelevant to the model's input-output behavior, and therefore we expect input-output invariance under this particular intervention. So two very different causal models with the same intervention behind it. A related idea is replacing an actual representation with an average over a bunch of representations for some interesting subpopulation, maybe as a way of neutralizing some information. And we can think even more expansively than this. For example, many kinds of data augmentation could be cast as interventions on model inputs. For example, if I go in and replace tokens in the inputs with synonyms for those tokens, my high-level causal model is probably one of label invariance under those synonym substitutions. And we could think even more expansively about this. As I said before, this is a thriving area of the literature, and many exciting model explanation methods are in fact intervention-based methods. So lots of innovative things are happening in terms of the causal models that we're testing and the kinds of interventions that we perform. But I want to take stock a little bit when it comes to causal abstraction in particular. I don't have time to review these findings in detail. The headlines are kind of as follows. On the one hand, we've used this method to find really interesting evidence that models are encoding interesting linguistic and human-level concepts, especially in the area of compositional semantics and discourse semantics. On the other hand, so far we've applied these methods only at the scale of models that are kind of like BERT and BART, whereas the most important models for today are typically an order of magnitude larger. And that is kind of stemming from the fact that the method as I presented it to you so far is not especially scalable. I think we've got verifiably faithful explanations with causal abstraction. They're human interpretable via the high-level causal model, and they're certainly causal in their nature. I haven't talked with you about improving models yet, but I'll do that in a second. But I am worried about scalability and also about the assumptions we're making about how information is encoded. So I've given those some frowny faces for now, but at the end of the talk, I'll try to turn those frowns upside down. But let's first turn our attention to improving models. This will be a relatively straightforward extension of causal abstraction that we call interchange intervention training, or IIT. Here's how the method works. On the slide here, I have a summary of the interchange interventions we were performing before to test the alignment between S1 in the causal model and L3 in the neural model. And the twist here is that the intervention failed. We were hoping to get output 14 when we intervened on the neural model, but it instead computed 4 under that intervention. Now, we could feel sad about this because our hypothesized causal model is false for this neural model, but we could also see it as an opportunity. After all, the difference between what the network predicted and what we wanted is an error signal that we can use to update the model parameters and potentially improve it. And the process there is kind of interesting. So we get gradients flowing as usual back from the root to L1, L2, and L3. And from L1, they flow back to the inputs as you would expect, and the same for L2. But for state L3, where we intervened, we have a kind of interesting double update coming from both the source example over here, its computation graph, as well as the base example that we're operating on. So a kind of double update, and the overall effect of doing these updates repeatedly is to gradually push that state L3 into alignment with S1. So whereas we didn't have a causal abstraction relationship before, we will obtain one as we do continued IIT in this way. And what we're doing, in effect, is inducing modular structure as given to us by our causal model. We've used IIT in a bunch of different settings quite fruitfully. For example, we used it on the MNIST pointer value retrieval task to good effect, as well as on Rescan, which is a grounded language understanding benchmark. We also applied IIT in the context of model distillation. Here we're augmenting the standard language model distillation objectives with a new IIT objective designed to ensure that teacher and student internal states play the same causal role. That's a productive distillation method, and it also shows you that the causal model behind IIT could be quite abstract. We've also applied IIT in the context of inducing internal representations of characters in language models that use subword tokenization. The catch here is that subword tokenization models are great language models, but they have only partial knowledge of the characters in their tokens, which is a blocker for many character level tasks. With IIT, we can induce that information in the internal representations to good effect. And we have also used IIT in the context of what we call causal proxy models, which are interpretable models helping us understand how otherwise opaque models are operating. So let's return to our scorecard. We keep our smileys for causal abstraction, and we now have a smiley for a path to improving models as we go from causal abstraction to interchange intervention training, a small step. But we're still worried about scalability and information encoding, so I'll address those frownies in the final part of the talk. Right, so the final method that I'll talk about today is what we call boundless distributed alignment search, boundless DAS. This is our leading contender for a scalable, robust causal abstraction method. Before diving into the method itself, let's just unpack a little bit why we're worried about scalability and information encoding. For scalability, the blocker is really that alignment search is expensive. For even a modestly sized causal model and even a tiny neural model, there are astronomically many ways that you could align variables in the causal model with subsets of neurons in your target model. So the result is that for realistic problems, we have to do a lot of heuristic pruning of that space, and we are very apt to miss good alignments and come up with false negatives. The information encoding assumption is actually similar. Here, the concern is that we have so far in the classical mode searched only in a standard basis, which really amounts to saying that groups of neurons will play unique roles, even though we know from the model explanation literature that neurons can play multiple roles. And so with boundless DAS, we are really hoping to address both of these problems at the same time. To make boundless DAS vivid, I want to work with an even simpler toy example from before. So now we've got Boolean conjunction. Our causal model is given in gray here. We have the Boolean variables come in, it stores those in intermediate values, and then outputs Boolean conjunction. And in purple here, I have a neural network that, with these parameters, perfectly solves my Boolean conjunction problem. If I want to prove that the gray model is a causal abstraction of the underlying purple neural model, I first hypothesize an alignment. And so here's a very natural alignment where I align the inputs as you would expect, I align the outputs as you would expect, and then I do what seems like a natural thing of aligning V1 with H1 and V2 with H2. Here's the twist. The high-level model does not abstract the new neural model under our chosen alignment. And let me just give the game away for you. Here's a spoiler. I made a crucial mistake, so to speak, when I set up this alignment. I should have aligned V1 with H2 and V2 with H1. A simple mistake. It's meant to simulate the scenario where I have a very large causal model and very large neural model, and I can only search a subset of the alignments. And this might show for you that I could easily pick the wrong subset and therefore miss crucial structure. And just to round this out, here's a kind of example showing that the interchange intervention fails. I do the standard thing of intervening on the causal model, and I get true as the output. When I do the aligned intervention on the neural model, it predicts a negative number, which we're construing as a prediction of false, and therefore we have unequal counterfactual predictions and a failure of our causal abstraction analysis. But I already told you what the problem was. I picked a wrong alignment. And the question is, could we be robust to that kind of simple oversight? The answer is yes. And the essence of this is that our abstraction relationship doesn't hold in the standard basis that we've been looking at. But if I simply rotate H1 and H2 by negative 20 degrees, then I do get a perfect causal abstraction relationship The trick here is that what in effect happens when I perform that rotation is that I swap the roles of H1 and H2, and my previously problematic alignment is now perfectly fine. And that is the essential insight behind boundless DAS. With boundless DAS, we freeze the target model because we're trying to explain it, but we learn a rotation matrix and boundaries for the intervention site that maximize interchange intervention accuracy. So this is essentially like IIT, but in the service now of learning this explainable rotation matrix and its boundary parameters. So now we can take stock. We have our smileys from before because we have a strictly more expressive method in boundless DAS, but it's now scalable because we've replaced all of the alignment search that we were doing before with a process of learning a rotation matrix and those boundary values. And we just do that by standard optimization techniques, no more brute force search. And at the same time, we've dropped our assumption about how information will be encoded because now we're performing these rotations, allowing neurons to play multiple roles under different rotations and essentially saying that the crucial information might be stored in a non-standard basis in this network, which is entirely plausible. The standard basis is natural for us as humans, but there's no reason to presuppose it for these complicated neural models. So I would love to talk with you in detail about the ways that we're applying boundless DAS now, but time is short, and so let me just make a pitch for you to check out our new paper, Interpretability at Scale, Identifying Causal Mechanisms in Alpaca. This is us using boundless DAS to study alpaca and come to an understanding of how it does in-context learning. We find that alpaca has found a really interesting structured solution to the problem that we're studying. And I think this paper also shows that boundless DAS does indeed scale to models that are at the level of alpaca, which has 7 billion parameters. And really, the only blocker to applying it to even larger models is our own compute budget and access to those models. So let me wrap up. First, I wanted to just remind you of those high-level goals that were guiding us. We want models that are safe, trustworthy, and that we can control in lots of interesting ways. And it seems to me that all of these goals depend on us having really robust explanations for model behavior. And that is really the guiding motivation for doing this explainability research for me. It's a thriving area, lots of progress. I thought I would just make some predictions about things that we'll see in the near future in this space. First, I'm certain that we'll see deeper causal explanations from these methods, and that they'll be more illuminating in terms of operating at the level of human interpretable concepts, which will be more helpful for those goals that I described before. I also think we'll see automatic discovery of causal models that will remove a blocker that we currently experience where we have to hypothesize a causal model rather than finding it in a kind of free-form way. If we can find them in a free-form way, then a whole new space of hypotheses will open up for us. We'll also see applications to ever larger foundation models, to the most important models that people are using today. And then finally, I think, and this is inspiring scientifically, we're going to see increasing evidence that our models are inducing relevant causal structure about our world, an incredible finding about how these models are increasingly robust and what data-driven learning can teach a model about the world that we live in. Thank you.